Hello, my name is Shaiban Ahmed, and I welcome you to our presentation on an adaptive strain estimation algorithm using a short-term correlation technique. Ultrasound elastography is based on the estimation of strain due to applied tissue compression. Conventional strain estimation techniques based on the cross-correlation of pre- and post-compression signals are known to use large kernels, which are major sources of decorrelation noise. By large kernels, we mean a kernel having axial length of 2 mm for a dataset which is about 37.5 mm long in the axial direction. Strain maps generated using these conventional large kernels are known to have low signal-to-noise ratio. Short-term kernels were used previously to reduce this decorrelation noise. Now, adaptive stretching, where the post-compression signal is stretched temporarily to increase correlation, have also proved to be a good estimator of strain. In our work, we maintain that adaptive stretching, if implemented using short-term cross-correlation kernels, can lead to significant reduction of decorrelation noise and have higher signal-to-noise ratio compared to the classical approach. Now let's look into our proposed algorithm. For our analysis, we have used RF scan converted in vivo patient data of breast tumors. First, for each data point, we compute an array of overlapping short-term kernels. Each short-term kernels are about 0.5 mm long, and they have around 75% overlapping between them. In total, the array of short-term kernels covers a total length of 2 mm in the axial direction. Similarly, from the post-compression signal, we compute an array of overlapping short-term search windows. Each search windows are about 2.1 mm long. Computation of cross-correlation between the respective short-term kernels and short-term search windows gives us an array of short-term cross-correlation functions. The mean of this short-term cross-correlation function is then computed, which gives us one single mean cross-correlation function. The location of the true peak is obtained from this mean cross-correlation function. Based on the location of true peak, a stretch factor is applied to the data. The post-compression signal is stretched temporarily using this stretch factor to increase the cross-correlation between the pre- and post-compression signal. Different stretch factors are applied to the data using adaptive means, and the peak of mean short-term cross-correlation function is calculated for each stretch factor. The stretch factor that yields the highest peak is used to calculate the strain for that data point. Now let's watch a short animation which attempts to visualize our proposed method compared to the traditional one. In the short-term cross-correlation functions, several false peaks along with the true peak can be present at different locations, but the true peak will always be in the same location. Hence, taking the mean would lead to the true peak rising above all the false peaks in the mean short-term cross-correlation function. From this mean short-term cross-correlation function, we can find the location of the true peak. We have selected the desired length of short-term kernels as 32 sample points or 0.5 mm long axially. Size of the short-term kernels was determined using an empirical analysis. We tried out different combinations and based on factors such as the maximum value of the cross-correlation function, contrast to noise ratio, signal to noise ratio, and also based on visual observation, the size with the best output was considered. We considered the accommodation of both positive and negative maximum displacement while obtaining the preferred size of the short-term search windows. Our dataset is 2,500 samples long axially, and the applied strain is about 2%, and hence the maximum possible displacement is around 50 samples. Considering both positive and negative displacement, the total size of our short-term search windows become 132 samples or 2.1 millimeter. We compute 13 short-term kernels and 13 short-term search windows for each data point. The successive short-term windows are obtained by taking an axial shift of 8 samples or 0.125 millimeter. It allows us to have around 75% overlapping between successive short-term kernels. The size of this axial shift was determined based on an empirical analysis. We estimate strain using adaptive means. A stretch factor is applied to the data and we stretch the post-compression signal temporarily using that stretch factor. We repeat the steps of short-term cross-correlation using the pre-compression signal and the stretched post-compression signal. And then we calculate the peak obtained from the new mean cross-correlation function. In this way, different stretch factors are applied to the data based on adaptive means. Peak of the mean cross-correlation function is calculated for each stretch factor, and the stretch factor that yields the highest peak is used to estimate strain. We calculate the next strain by using the next set of short-term windows. Now let's look into a comparative assessment between the conventional method and our proposed one. The top two strain images are generated using classical approach, while the bottom two images are generated using our proposed algorithm. As you can see, our proposed method leads to better strain images with lesser decorrelation noise and higher contrast. The lesion boundaries are also sharper with enhanced visual appearance. Results and conclusions. Visual depiction of the strain maps generated using our algorithm appeared to be better while compared to classic strain estimation using large correlation kernels. We can also note an improvement in signal-to-noise ratio by 5.12 decibels and contrast-to-noise ratio by 11.52 decibels. Lesion boundaries have appeared to be sharper, while we managed to obtain strain images with better contrast. Problems, limitations, and future works. Our proposed method does require slightly higher computational time. Also, total noise removal was not possible. To address these problems, we are working on implementation of our algorithm using 1.5D approach, which includes a lateral search. Also, we are trying to apply adaptive spectral stretching to our algorithm. Before we end, here you can find the information of all the authors who have contributed in this work. And if you want to know more about our work, you can reach out to us by using the following email. Thank you so much for your patience. Have a good day.